you get infinity on the top, you get infinity on the bottom. And so you can differentiate. Right? Use L'Hopital's rule. By L'Hopital's rule, this is going to be the limit of kx to the k minus 1 over 2bx natural log 2. Right? Well, as x goes to infinity, that's still going to infinity, and that's still going to infinity. So you use L'Hopital's rule again. And you use it over and over until you get down to a number, k times 1, k times 2, down to 1. And on the bottom, you're going to get 2bx natural log of 2 to the k. Right? So you do this k times. You apply L'Hopital's rule k times in a row. And then you see what happens. Right? As x goes to infinity, what happens? Well, this is a constant.
Yeah.
You have 2 to the x on the bottom, so it becomes 0. Right? You get, it's a big constant, but it's still a constant, and the bottom becomes infinite. So you get 0. So the answer is 0. Another example, the limit of n to the 1 over n. The limit of n to the 1 over n. Again, that's going to be the limit as x goes to infinity of x to the 1 over x. Okay. For this one, you do something tricky. You say, I know that you evaluate the natural log of the limit of x to the 1 over x as x goes to infinity. Right? Because of continuity, you can pull the limit, you can pull the natural log through. So since ln is continuous, right? It's a continuous function, so I can pull the limit. I can pull the limit out and put it back in either way. Limit passes through the continuous function. You might be wondering why we brought this natural log in. It's because now we get a natural log of x over x as x goes to infinity. Right? Right? And now we can use L'Hopital's rule on it because we get infinity over infinity. Right? Infinity over infinity. But we saw this, we actually did it already. It turned out to be 0. Right? I mean, using L'Hopital's rule, you get the limit of 1 over x over 1 as x goes to infinity. That's it. Right? Okay, so we figured out that the natural log of this thing was 0. So what's this thing? If the natural log of this limit is 0, what's the limit? 1, right? B1. Right? The natural log of it we figured out was 0, so this thing is 1. Okay, so that's actually a pretty important limit, that the limit of n to the 1 over n is 1 as n goes to infinity. Okay, last example. The limit of 1 plus x over n to the n as n goes to infinity. Actually, let me use a different number here. I'll call this delta. Okay. So again, we're going to switch this over to a function 1 plus delta over x, quantity to the x, as x goes to infinity. Right. I mean, after a while, you sort of give up on switching it over. You don't really need to switch it over to x. You could just keep it as n and imagine n is a continuous variable. Okay, so you look at this thing, and again, we're going to play the natural log game. Let's evaluate the natural log of the limit. You know, to even make it simpler, let me just, instead of using delta, I'm going to use 1. We use 1. And you know what's going to happen. We said this earlier. This is going to turn into e. So this is going to turn into 1. Okay. So again, we're going to play a natural log game. The limit as x goes to infinity of the natural log of 1 plus 1 over x times x. Right? The natural log of this to the x power, but we can pull the exponent out because it's a logarithm. Right? We should have the x here, but we can pull it out because it's a logarithm. Okay, so, and we're going to do something funny. Sorry, maybe I'll do it here. The limit, we're going to write this as the limit of 1 plus 1 over, a natural log of 1 plus 1 over x as x getting divided by 1 over x. Right? And you see why I'm doing that, right? Because then I'm going to get 0 over 0. Right? Since it's 0 over 0, I can use L'Hopital's rule. Anyone confused? Okay, so what do? You differentiate the top and the bottom, right? So you get the derivative of this thing, right? That's negative 1 over x squared over this thing over the derivative of this thing. Right? The derivative of this over the derivative of this. Right? The limit of that as x goes to infinity. You see what happens? This and this cancel off, and as x goes to infinity, this becomes 0, and you get up with 1. You end up with 1. Okay, and so since the natural log, right, the natural log of this thing was 1, this thing is going to be e to the 1. Let's just say e. Right? So that's also very important. As n goes to infinity, 1 plus 1 over n, quantity to the n, turns into e. If we had kept the x here, this would have been e to the x. You can do that as practice if you like, but it follows exactly the same argument. But you see why I changed it to delta, because we're using x as the variable. Maybe when you do it, use delta instead of x. Okay, so that's it for today. I sent out the modified homework I think. But I think I'll have to change it a little bit more because we didn't finish all of 8.1. So I will do the first few problems, but then if there, I'll try to fix it later. Okay. But the first few problems should be okay. Oh, I forgot. There are exams to hand out. Okay. Maybe we'll start the next class with questions on the exam. So,